Hello and welcome to another presentation on congruent triangles, congruent proofs and similar solids. Now we're going to be looking firstly at congruent triangles. Congruent triangles naturally are exactly the same shape and size. They're to be contrasted with similar triangles which are exactly the same shape but not necessarily the same size. Essentially similar triangles are just a scale factor enlargement or reduction, whereas congruent triangles, well, they've got a scale factor enlargement of 1 if you like. They are exactly the same shape and size. Now, the congruence proofs for triangles are probably the most difficult bit to master in some of the, well, not the most difficult bit actually, because some of the circle theorems geometry is pretty tough as well, but it's a tricky bit of a geometric proof for the students to master in GCSE, and it's worth us going through the 4 ways of proving two triangles are congruent. There are essentially 4 different ways of doing it. You can argue side, 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 by which I mean we have 3 sides all of the same length, 3 pairs of side all of the same length. You can also argue right angle hypotenuse side. I think that really is just a special case of part A, but I'll explain why about that in a second. You've also got C, angle side angle, 2 angles and a corresponding side. Very important that the side is corresponding, and I'll explain a bit more about that in a second. And then finally, and I've deliberately put this one last, you've got SAS, 2 sides and the angle included. Now, what's an included angle? Well, it just means the angle between 2 sides. This is often the case actually in GCSE maths, that we want 2 sides and the angle in between. For example, with the formula for the area of a triangle, half AB sine C, you need 2 side lengths and the angle in between. Funnily enough, you also need the same thing in cosine rule, where if you've got 2 lengths and the angle in between, you can find the third length using cosine rule. So this idea of 2 sides and the angle in between comes up actually in a lot of different contexts. Okay, let's have a little look on GeoGebra to demonstrate some of these ideas, why these 4 different ways of proving 2 triangles are congruent, why they actually work, why they guarantee that the 2 triangles are exactly the same shape and size. Okay, I'm going to look firstly at these 2 triangles, and I'm going to demonstrate the property of SSS with this first one on the left. Now, why is it side, side, side is enough to prove congruence? Well, let's try and move this one. I've deliberately made sure in this triangle that 2 of my lengths are always going to be 4 and 5, and the third length, the length between A and C, varies. Now, if I wanted this side to be length 3, I'm just going to try and find it exactly. Almost got it. There we go. I obviously have, actually it's a right angled triangle, this will be a Pythagorean triplet, 3, 4, 5. Now, if I try and move this so that the triangle's angles stay the same but the lengths change, you'll quickly see that it's impossible. I can actually put one of the angles, let's just put the angle at C on this diagram, 53.1. If I try and change that angle but not change the length of the side, it's actually impossible to do. The only way I can do it, if I move it over here, let's just move, oh, I don't want to move that, sorry. Let's just try and click on that point again. If I try and move it over here, I actually end up with exactly the same triangle. I'm just going to change where that angle's appearing. I actually end up with exactly the same triangle just on the other side. It's a 3, 4, 5 triangle with that angle at 53.1. Essentially, and it's normally quite nice for the students to see this, if you try and change any of the lengths of those sides, you will change the angles as well. And so side, side, side is sufficient to show that the 2 triangles are congruent. They're definitely the same size because they've got 3, 4 and 5, but they're also definitely the same shape as well because the angles do not change. I'm now going to do a similar thing, but well, actually first I'm going to talk about RHS. RHS, I think, is just a special case of SSS, because if I've got a triangle, and I'm just going to draw this for the sake of speed, with a right angle, and I've got a hypotenuse, let's say it's 10 centimetres, and I've got a side, let's say it's 6 centimetres, then surely by Pythagoras' theorem I can work out this third side, and I'm sure you've already worked it out. The third side is going to be 8 centimetres. I can immediately establish that from two sides, a hypotenuse and the other side, using Pythagoras' theorem. So right angle hypotenuse side I think is just like SSS, because we can find the third side with Pythagoras' theorem. And so that's definitely sufficient to show that the two triangles would be congruent. If we had two triangles and we could pair up, they've both got a right angle, they've both got a hypotenuse of 10 centimetres, they've both got a side of 6 centimetres, that is sufficient to show that it's a congruent triangle. I'm now going to show the same thing but with angle, side, angle. So I'm just going to annotate this, angle, side, angle. Now as you can see, I've got two angles and I've got a side in between. Now the side doesn't have to be in between, and I'll tell you exactly why that is. It's because if you've got two angles in a triangle, you've actually got a third angle as well, because you can just do 180 minus the first two angles to find the third angle. Therefore, the side doesn't have to be in between the two angles, but, and there is a but coming, it must be the corresponding side. So if I could now just draw another triangle, and this diagram's not going to be to scale, and I'm going to have 78.4 here, just like that one has, and I'm going to have 72.2 there, and I'm going to have my 4 centimetres if you like, over here. These two triangles here would not be congruent because the side is not corresponding. It must be a corresponding side. Clearly, whatever length this is, let's find out what length it is. Let's show the label there. Oh, how convenient, it's 8, yeah? This triangle could just be twice as large, therefore, as the triangle below. In fact, it looks like it will be, because it'll have exactly the same angles, but that corresponding side seems to be twice as large. Now these triangles would merely be similar then and not congruent, and that's why the side must be a corresponding side in ASA. So be very careful with that. Now finally, the last one I want to show you is something which is often called the ambiguous case. Now that is SAS. SAS only works if the angle is included, yeah? And when we talk about an included angle, we just mean that the angle is in between the two sides, yeah? Now this is a classic example of a triangle which is not SAS. This would be a triangle, if I can just show you two triangles, I've got a side here of 7 and 5 centimetres if you like, and then an angle of 20, and then I've got 7 and 5. Once again, the diagrams are never to scale necessarily, and I've got an angle of 20 in between. These two would qualify as being congruent because they are SAS. But what I want to show you is why the angle has to be in between and can't just be on the end. This diagram shows you perfectly why that is the case. Look at this diagram and you will see that if you have a triangle with length 5.03 on one side, 7.36 on another, and the angle at the end, actually there's two different, completely different shaped triangles which qualify as having two lengths, 5.03, 7.36, and an angle on the end of 40 degrees. You can consider this something like SSA. SSA doesn't work for congruence, and this is why. If I just move this over here, you can see I've got a smaller triangle, CBD, and a larger triangle, BDA, both of which have lengths, two sides the same, and an angle on the end the same, but which clearly aren't congruent. Why aren't they congruent? Because one's smaller than the other one for a start. One looks to be about half the size of the other one, and therefore SSA or ASS, they're not enough to show congruence. I hope that makes it clear. Now, that's well worth remembering, but let's actually look at this in the context of an exam question. 1 second, let me start my presentation up again. Okay, let's actually look at this in this presentation then. What we're going to try and do, we're asked to show, it's just a parallelogram, and we're asked to show that ABD, so maybe if I can just draw a line across here, oh no, I think I'll have to go back to here, let's just clear that. I'm going to show that, oh, that's a very unstraight line, isn't it? Let me just try that again. There we go, steady hands. Okay, we've got to try and show that triangle ABD and BCD are congruent. By the way, there is a way of showing congruence mathematically. It's the 3 equals sign. That's congruent. Okay, they don't have to know that, but it's nice to show them things. Just because they don't have to know it doesn't mean they should know it. I think always figure show them as much as you can. Now, with a congruence proof, you must sort of argue and give reasons for your argument at each stage. Now, first thing I'm going to argue is that BD is common to both. Yeah, it's on both triangles, and therefore I've established that 2 of the sides are the same. And I always put in brackets at the end of my argument S or A or R, depending on what I've just shown. Now, I haven't really established anything there. I don't really need much of an argument for that because BD is common to both triangles. I also need to argue that I'm going to try and do side, side, side here. So I'm going to now argue that AD equals BC. Now the reason for this, and I can only use the reasons they've given me, the reason for this is that ABCD is a parallelogram, and parallelograms have equal length opposite sides. So parallelogram, oh, my spelling can be quite bad. Parallelograms have equal sides opposite. And then finally I'm going to make exactly the same argument. AB equals DC. Oh, by the way, I should have put my S there because I've shown another side is equal. And now I'm going to do, oh, AB equals DC. I apologise for that. AB equals DC, and that's a third side. Yeah, and it's for exactly the same reasons as the one above, so I'm just going to put ditto there. And then at the end I can say, hence, they're congruent. And that completes the proof. Now, it is possible to argue in a different way that they're congruent, but if you don't mind, I just want to show you definitely something which is false. What a lot of students do when they see this line up here is they try to argue that angle ADB equals BDC. And that is not true. The reason it's not true is that parallelograms, if you take the diagonal in a parallelogram, it doesn't necessarily bisect the angle. A good example of why a parallelogram's diagonal doesn't necessarily bisect the angle is if you take a rectangle which is really long. I'm sure you can see if I take the diagonal there that that angle is nowhere near as big as this angle. And a rectangle is indeed a special case of a parallelogram. It has 2 pairs of parallel sides. So they can't assume that an angle is equal to another angle. You can only use what you're given. Now it would be possible, of course, to argue that ADB equals another angle, and I'm just going to show you which angle, because what we do have here, oh, sorry about that, what we do have are parallel lines, and so we do have alternate angles here. Yeah, so ADB actually equals, and I've labelled the wrong one here, I can see. If I just quickly clear it again. Oh, well, let's actually use this one. It's easier to see, I think. That the students often call these Z angles, but I prefer it if they call them alternate angles. But we could argue that angle ABD equals BDC. When students try and do this, I say that's absolutely fine, but I think you're making it tougher for yourself than you actually need it to be. It's always easier to argue side, side, side. It's always the easiest one if you can do that. But if you can't, then you can do it another way. Once we've done that, so we've got an angle here, which is great. We could also argue that we've got another angle for the same reason. We could argue that DBC equals angle, now if you look, I'm arguing this angle is going to equal, I'll put a double line there just to show, that's going to equal angle ADB. And I've got another angle, and by the way, I've been very bad, I haven't put my reasons down, so you need to put down alternate angles. And once again, alternate angles, I don't mind you going ditto there. Now we've got two angles. Now the rule is that if you've got angle, angle and a corresponding side, you're okay. And then you can say, why not use just BD is common to both again. And you've got a side that they have in common. It's definitely the same corresponding side because it's between the same two angles. And then you can say at the end, hence congruent. And it completes the proof. Let's have a look how that works in one of the examples which you did in the first past paper. Because I know this one often catches students out, and I'm not surprised, to be honest, because it's quite a difficult question. Let's just zoom in on it. Oops, sorry. Okay, here it is, just after this one. Okay, you might recognise this question. Here we've just got to prove that ADC is congruent to ADB. As I've got the fact that AD is perpendicular to BC, it's going to be relatively easy for me to argue that BDC is 90 degrees, and that's because of angles on a straight line. Adding to 180. Angles on straight line. Please do write more than just angles on straight line. They're very pernickety about this, examiners, and you don't want to give them any reason to take the marks off. Add to 180 degrees. And you're good, yeah? Once you've got that, we can just say AD is common to both. So we've got a side. And we can say BDC equals ADC. So we've got actually a right angle, so I'm going to call that R, and I'm going to use RHS here, and AB equals AC. Why can I say that? Because they told me it was an equilateral triangle. Yeah, and so I can just say, and that's a hypotenuse, clearly. And therefore, congruent. And it's done. Okay, I hope that makes a bit more sense out of congruence proofs for you. You always use one of those 4 rules and use them carefully. Try and use the easier ones and be careful with that SAS rule. Just remember that the angle must be in between the two sides. Let's now take a look at similar solids. Which is about area scale factor, linear scale factor and volume scale factor. Okay, what I'm going to do, I'm just going to find my presentation, sorry about this, taking a little bit more time than I was hoping. Okay, let's go to, okay, so let's talk about similar shapes. What we need to bear in mind with similar shapes is that when two solid shapes are similar, one is a scale factor enlargement of the other. But bear in mind, linear scale factor, area scale factor, volume scale factor, they're not all the same. Let me give you an example. Here I've got a cube. On my cube, I've got lengths of 2, 2 and 2, and so the volume is going to be 8. Let's take another cube. Let's take a cube of 6, 6 and 6. This cube will have a volume of 6 times 6 times 6, which is 216. Now notice here, we've trebled the lines. But what's happened to the volume? The volume has been multiplied by 27. And you can check that on a calculator if you like. And that is because of this. Linear scale factor cubed equals volume scale factor. Linear scale factor squared equals area scale factor. It's always important to ask yourself when something's been enlarged, what's been enlarged? Have all the lines been enlarged? Or have all the areas been enlarged by that scale factor? Or have the volumes been enlarged by that scale factor? Because if you double all the lengths in a shape, you're going to have increased the area by 4. Because 2 squared is 4. If you take a solid shape and make it, let's take a person maybe, if they grow to twice as high, then their volume should have increased by a factor of 8. It's as simple as that. Now let's actually have a look at an exam question using these principles. Let's get rid of that. Let's find the question that I was looking for. Okay, where was it? It's not this one actually. Okay, here it is. Here we're told x and y are two geometrically similar solid shapes. The total surface area of x is 450 centimeters squared. The total surface area of y is 800 centimeters squared. The volume of shape x we're given, and we're going to find the volume of shape y. And they don't tell us anything else about our shape. Well, that's okay. If I deal with linear scale factor, area scale factor and volume scale factor. Firstly, let's think about going from x to y. X is clearly the smaller one, y is the bigger one, yeah? My area scale factor, can you see that I've multiplied it by 800 over 450? And I get that scale factor just by dividing the surface areas, which I can easily cancel down actually, and it cancels down to something really nice. It cancels down to 16 over 9. I say that's really nice because I need to work out the connections between area scale factor, linear scale factor and volume scale factor. Now let me just quickly write it down up here. Linear scale factor squared is area scale factor, but linear scale factor cubed is volume scale factor. What it tells me is I always need to find the linear scale factor first. So that's what I'm going to try and do. As linear scale factor squared is area scale factor, my linear scale factor here will be the square root of the area scale factor. And that's quite easy to do, it's 4/3. That's why I was happy about the numbers, because this came up on a non-calculator paper, and well, you wouldn't want to be square rooting something ugly there. You want to be square rooting something which is square at the top and square at the bottom. Now, if my linear scale factor is 4/3, my volume scale factor is going to be the cube of that, and 4/3 cubed, well, that gives me 216 over 27. I can now work out the new volume. The volume of shape X is 1350, so what I'm going to have to do is 1350 multiplied by 216 over 27. Okay, I just wanted to check, but actually it is a calculator paper, you'll be pleased to hear, because I thought actually this looks rather tricky at the end, but we can do it without a calculator. I just want to show you. This is the same as 1350 times by 216 over 27, and the good news is that 27s actually go into 1350 quite nicely, and that's because 2,700 is exactly double 1350, yeah? And therefore it's going to go into it 50 times. So you can do just 50 times 216. We can then think of that as 100 times 200 times 216 and halve it, and therefore we get the answer 10,800 centimetres cubed, and it's done. These questions are quite tricky. Be careful with linear scale factor, area scale factor and volume scale factor. I always think of it like this myself. It's the way my old maths teacher at school taught me to do it. I'd never see other colleagues in my department actually using the same kind of notation with LSF, ASF and VSF, but I quite like it. It summarises things nicely for me. Okay, I hope that's been really useful. Good luck with the congruency proofs and the similar shapes. Please, please, please don't hesitate to email me if you're stuck on any of these ideas. I can always get back in touch with you and hopefully give you a hand. Okay, thank you for listening, and you will be hearing from me soon, no doubt. Bye-bye.